Awesome. So I'm going to be talking about quantum machine learning using Covalent, which you saw presented earlier today, and an application of a quantum algorithm called QAOA. So just some quick background on me. I'm a quantum software engineer here at Agnostic. I received my PhD in astrophysics from the Department of Physics and Astronomy at the University of British Columbia, which is in Vancouver, where I live now and where I'm speaking to you from. But I got my undergraduate degree from RPI actually in physics. Okay, so before we talk about quantum machine learning, we're going to do a brief introduction to quantum computing. So quantum computing kind of finds itself at this intersection of a few different disciplines. There's computer science, there's physics on the quantum mechanics end, there's math, and there's engineering, and quantum computing brings all of these together for this new kind of computation. So far, quantum computing already has a lot of applications across different fields, ranging from cryptography, which actually has some connections to its origin, to biology, drug development, even finance, and data science and machine learning, as we'll see today. Okay, so if we looked at a timeline of quantum computing, and this is an incomplete timeline, it would be pretty short. Things have really gotten rolling in the past couple of decades. But if you wanted to be, really complete about it, you might want to say that it starts with the first programmable digital computers. So the first computer similar to classical computers that we have today, which was ENIAC in 1945. Then if you wanted to be really complete about it, you might want to date back to the discovery of quantization by Max Planck in 1900. But I'm just going to focus on the more modern timeline of quantum computing. So there was some talk that went on between, the discovery of quantum mechanics and the first, real developments in quantum computing. So for example, in the 1980s, Richard Feynman suggested that we could develop a computer that could time evolve quantum states. But the ball really got rolling in 1994 with Peter Shor developed his Shor's algorithm, which is an algorithm that shows that quantum computers can factor numbers exponentially faster than classical computers, which had implications for cryptography. So it might take millions of years for a classical computer to crack a crypto system, whereas a quantum computer theoretically could do the same thing in a few hours. So this really gets the ball rolling with the theoretical end of quantum computing, and then we start having the first quantum processors in the late 2000s. So in 2009, Yale creates the first solid-state quantum processor. A few years later, a company here in Vancouver, actually called D-Wave, develops the first commercial quantum annealer, which is a sort of different kind of quantum computer we'll touch on briefly. In 2013, Google launches its quantum AI labs. It turns out to be a pretty big move, as we'll see in just a second here. And in 2017, we start getting more advanced hardware with more qubits from Harvard and IBM. Next year, in 2018, our company Agnostic was founded. The following year, Google was able to claim quantum supremacy in a particular application. So it sampled instances of a quantum circuit about 1 million times in just 200 seconds. And they estimate that state-of-the-art classical supercomputer would take about 10,000 years to do the same thing. A year later, Amazon Bracket becomes available, which is a cloud resource that connects users to different quantum hardware devices. And just this year, Xanadu announced a quantum supremacy claim, similar to the Google claim, where looking at a sort of narrow application, it looks like quantum computers are able to do something that classical computers can't do on a reasonable timescale. Okay, so to get a feel for what quantum computers are, we have to first lay down the foundation of classical computers, which is a bit. So a bit can take on a value of 0 or 1, whereas quantum computers are composed of quantum bits, or qubits for short, which are in a superposition of 0 or 1. So they can be somewhere in between both values. We represent this geometrically on the Bloch sphere. So if we have a state of 0 on the North Pole and a state of 1 on the South Pole, then our quantum state in our qubit can be some linear combination of these two states with these prefactors C0 and C1 that would determine the probability of it being in either state. So classical computers would give you deterministic measurements, so it's either a 0 or a 1, whereas a quantum computer will give you a probabilistic measurement. In a classical computer, if you have n total bits, that means you have 2 to the n states that you can only execute one at a time, or if you're doing parallel computing, you can execute them in parallel. Quantum computers are a bit different. If you have n different qubits, then you can encode all 2 to the n components into one quantum state simultaneously. Okay, so there's two main types of quantum computers. We're going to be dealing with gate-based computers in the tutorial today, but there are also quantum annealers. So gate-based computers have more broad applications. They apply gates or quantum circuit operations to your quantum state or your qubit, and they're a universal computer. Now, quantum annealers can answer a pretty narrow range of problems, so they answer optimization problems. And what they do is they search an energy landscape encoded as a Hamiltonian, looking for the lowest energy solution. So for example, if you're trying to optimize a cost function, you can encode that into a quantum annealer, and that can find something close to the minimum of your cost function. Okay, so you would have a classical NOT gate for a classical computer that could flip the value of a bit from 1 to 0. Quantum physics is a little different. You would use the language of quantum physics for a quantum computer, which is linear algebra. So instead of a classical NOT gate, you would use a Pauli X gate, which might look familiar to you as the Pauli X matrix. There's some other familiar gates here. So that's all of the Pauli matrices that perform different rotations, or in the Pauli X gate, it performs the flipping of the qubit. And here's some other really common quantum gates that you can apply in a gate-based circuit. There's a Hadamard gate. So if you start with a quantum state of 0, for example, and you apply the Hadamard gate, then you put that bit in a superposition of being both 0 and 1 with half probability of either. There's the controlled NOT gate, or the C0 gate, which will entangle and unentangle 2 quantum bits or qubits. And then there's the Foley gate, which is the same thing, but with 3 qubits. Okay, so when you're building a quantum circuit, you have your qubit represented as a wire. So on the left is our initial state, and then we have the gate that we apply, which is here our Pauli X gate, and then what we use to make the measurement, which here is going to be the Pauli Z gate. So using the language of linear algebra, it would look something like this, where we have our vector 1, 0, that's our state 0. We apply our matrix, the Pauli X matrix, and that just flips the position of the 0 and the 1 into state 1. And then when we're making our measurement of the Pauli Z matrix, what we do is we sandwich it in between the transpose of the vector and the vector itself. So that's computing the expectation value. If you're familiar with Broad-Ket notation, it'll look like this. We have our state 0, we apply our Pauli X matrix, that flips it, we get a state 1, and then we just sandwich it between the two states. Okay, so doing that in a quantum circuit, we would use penny lane. There's other tools that you can use, but we'll focus on using penny lane. We import it as QML for quantum machine learning, since that's what we'll be using it for. You can define your quantum device. Here we use a simulator known as default.qubit, and you specify the number of qubits that you want to do. Here, that's the number of wires. We set that to 1. Now, our circuit is constructed as a Python function, and we tell it to use the device or the simulator that we've designated by adding this little decorator to the top of the circuit function. So once we've said define our circuit, we apply our Pauli X gate, we specify which wire or which qubit we're applying it to. Here that's trivial, there's just the ones that we're going to specify, just that one. And then we return our expectation value or whatever else we're measuring in our circuit. You can build a more complex circuit. So here we have 3 different qubits, so we specify wires equals 3. we apply an X rotation gate to the first one, a Y rotation gate to the second one, and then a Toffoli gate that is entangling all three of them. And then finally, we're returning the expectation value of the poly Z matrix for all three. Okay, so I'm going to switch gears real quick and talk about quantum machine learning. So before I get there, and this might be familiar to some of you, I'm just going to briefly go over what machine learning is for example. So a machine learning involves developing a model to describe and make predictions about data, and your model parameters or hyperparameters are tuned using a data set. So if you have a bunch of data, you might split that into a training data set that is going to be used to train your model parameters so that they match the training data set. And then you'll use your test data set to see how well your model was able to make predictions about how the data would behave. So we do this by optimizing a cost function. So the cost function essentially is just measuring the difference between what your model is predicting and what your data is actually saying. And what you want to do is you want to minimize that difference so that your model is predicting something very, very close to what the data is actually saying, and you fine tune that by changing your model parameters. So on the left here, if we have these orange data points and we're trying to fit some quadratic function to it, we might be tuning our parameters describing that function, which is that white curved line fitting the data, until our cost function is minimized and we see that we get a good fit to our data. There's some pitfalls that can happen here. So on the left, we see an example of something called overfitting. So this happens when your model is too tailored to the training data and it's not really going to generalize well to test data. So that can happen when, like, say you add too many parameters and sure, your cost function is effectively 0. You have a perfect match to your training data, but it's maybe too perfect such that it's not going to work particularly well when you test it on your test data. And then underfitting can happen if, say, you don't have enough parameters. So if you're trying to do a linear fit to a quadratic function, it's not going to look so good. And then when we add our test data on the left, you can see we've overfit our model and it doesn't extend to include the test data. On the right, there's nothing that we can do really to get a linear fit to that model. We need to add more parameters. Okay, so there's two main kinds of quantum machine learning or machine learning problems. There's regression, which is what we've seen so far, which is fitting a model to data. And there's classification, which is taking features of the data and predicting what label it corresponds to. So that might be like some of these phones are really advanced. And if you're taking a picture of a cat, it might, as you're facing your phone towards your cat, it might come up with the label cat. And that's because it's been trained on a bunch of different photos of cats and it knows how to recognize which features correspond to the label cat. Or the same thing with dog. If you're taking a photo of a dog, it might know how to recognize, okay, these particular features we've seen in our training data correspond to dog, so it can recognize it as a dog. In this image here, we have the features being the X and the Y positions and the label being whether or not it's blue or purple. So our model would determine, okay, this particular point has these X and Y values that probably from our test data would correspond to it being blue. Okay, so we can think of 4 different kinds of machine learning algorithms. The most common kind is going to be classical data with a classical algorithm. So that's going to be the top left. But if you start incorporating quantum, you can get a situation where you have classical data and a quantum algorithm. You can have quantum data and a classical algorithm. And finally, you could have quantum data and a quantum algorithm. We're going to be focused on this kind, and in machine learning, this is going to be the most common, which is when you have classical data combined with quantum algorithms. And this is really going to be a hybrid process. So lots of steps are going to be classical. It's going to incorporate quantum circuits. We'll have quantum steps. And then some of the post-processing will be classical as well. Okay, so if you remember, when we're training our model, we're really training the parameters in the model, which means the model needs to have parameters that can be trained. So in that first circuit that we saw an example of, when we have a state 0 and we apply a quantum X gate to it and then measure it in the Pauli Z operator, there's no tunable parameters here. So that's not really a good circuit to use for a quantum machine learning algorithm because there's nothing that it can learn. It's just going to give the same thing every time. But if we add these rotation gates, Rx and Ry, they actually do take input angles. So these are tunable parameters because we can tune the different angles that we input into our circuit. Okay, so a quantum circuit with tunable parameters would consist of unitary operations, U of theta. So this theta is really important. It needs to have some kind of input parameter that can be tuned, performed on n qubits, the number of qubits in your circuit or the number of wires. So there's two really important things to go for when building a strong quantum circuit. You want expressibility, so you want your quantum circuit to be able to span a wide subset of Hilbert space, and you want entanglement. So entangled qubits are difficult to simulate using a classical simulator, and we see some indication that entanglement is a huge strength of quantum algorithms. Okay. So if we go to our block sphere, expressibility is its ability to span that sphere depending on what input parameters we give it. So for example, if we only have this RZ rotation, then we're only exploring around the perimeter, around the equator of our block sphere. So that's not super expressible. We can explore more of our Hilbert space. And it gets stronger once we add more rotation gates and we have additional angles to explore that Hilbert space. Now, entangled qubits, again, are difficult to simulate, but we see that they're presenting some kind of advantage. So an entangled quantum system is not the same thing as two separate quantum systems. So in that circuit, you effectively have two separate quantum systems. One is getting the Rx rotation, one is getting the Ri or Ry rotation, and they're not interacting. But if we add a Toffoli gate, now we've entangled our qubits, and now we have a system that is very different than if we just had three separate systems. Okay, I'm just going to grab some water real quick. So you may have heard that quantum computers are still in an early stage, and that's true. So we call this the NISQ era, the noisy intermediate scale quantum era. So noisy because these quantum computers are sensitive to their environment and they might lose their quantum state due to fluctuations that cause quantum decoherence. So this makes error correction really important in quantum computing. And error correction in quantum computing can't happen the same exact way that it would happen with classical computing. So if you're worried about losing your quantum state because of shorter coherence time, you can't just make a copy of that quantum state because of this no cloning theorem. And then there's also an issue with qubit connectivity where quantum computers today don't have all qubits connected to one another. Okay, so our application of quantum machine learning is going to be to the quantum approximation optimization algorithm, or QAOA. So QAOA is a method of finding approximate solutions to combinatorial optimization problems. So this is when you have a lot of different variables and you're trying to find some particular optimal combination of those variables. So they're very computationally expensive to solve exactly, both in terms of time and computational resources, which is why you would want to try to find an approximate rather than exact solution. It's also simple to implement and it can be run on these NISQ devices, so quantum computers as they are now. An example of the combinatorial optimization problem would be the traveling salesman problem. Some of you may have already been familiar with this. So essentially the traveling salesman problem is this problem where you have a list of cities and you know the distance between each pair of cities, and you want to find the shortest possible route that visits each city exactly once and returns home at the end. So problems like this, where you're trying to find some kind of combination to optimize some kind of function. So here your function is finding the total distance. So just to go over the math behind QAOA, first it involves some bit string Z. So each element in the bit string is binary valued at either 0 or 1 with n total elements in the bit string. The bit string is subject to some clause C. So the clause is equal to 1 if that element of Z satisfies your clause, or it's equal to 0 otherwise. And what you want is to maximize the clauses that are satisfied. So that's this clause satisfaction parameter to the right. That's just the sum of the total number of clauses. So the greater your value of CZ, the better your overall clause satisfaction is going to be. Okay, so in gate-based quantum computing, we would solve this by using Hamiltonians, or these time evolution Hamiltonians. So we use that to construct our quantum circuit using this U of H and T, where you'll have an input parameter in that time evolution operator that you can tune. So for QAOA, there's two different Hamiltonians. There's a cost Hamiltonian that finds the expectation value, or the expectation value of this cost Hamiltonian is the cost function to be optimized. So we want to minimize that value. And then there's a mixer Hamiltonian. So this is a layer that essentially increases the mix of the quantum state. So what it would do is prevent something from happening where you would only have the cost Hamiltonian, but when you go to calculate the expectation value, then the complex conjugate would cancel it out, and then you wouldn't be able to optimize it. So the mixer Hamiltonian doesn't commute with the cost Hamiltonian and essentially allows you to compute the expectation value, or you wouldn't otherwise be able to. So they look like this, and you notice both of them have these tunable parameters, these angles, gamma and beta. So a circuit for QAOA would look something like this, where first we start out with our Hadamard gate. If you remember, that's this common gate in quantum computers that takes a state and it puts it in a superposition of 1 and 0 with 1/2 probability of being in either one. We apply our cost Hamiltonian, and then we apply our mixer Hamiltonian. And this has it only applying once, but you can actually apply it multiple times using what's called variational circuit. What you would want to do is keep your circuit depth short. So that's keeping down the number of gates. And this is to avoid problems due to noise, because we are in this noisy era. Okay. So we'll use that to solve the minimum vertex cover problem, or get an approximate solution to the minimum vertex cover problem. So that is a combinatorial optimization problem to find the minimum number of vertices needed to cover all edges in a graph. And when I first read about this problem, I was extremely confused. So we're going to go over the picture just so we can see what exactly that means. So a vertex in this graph is just these circles, and the edges are the lines connecting them. So for an edge to be covered, that just means that it's touching one of the vertices that has been chosen. So in plot A, none of them have been chosen. We'd say they all have a value of 0. 0 edges are covered. That's not going to be a good solution. In graph B, 2 vertices are chosen, and now you can see all of the edges that are connected to them are highlighted in blue. So it looks pretty good, except we aren't actually covering all edges in the graph, so it's not going to be a great solution. If we go down to C, now we've chosen all but one of our vertices. All of our edges are covered. That looks good, but we have to remember that we're trying to find the minimum number of vertices needed to cover all edges. So that's what we get in D with this approximate solution, where we have these 2 different vertices and they're covering all of the edges in the graph. Okay. So we're going to solve this using a pretty fragmented process that I'll describe here, and I'll show some snippets of code before we actually go to the notebook. So we start out by defining a cost and mixer Hamiltonian, and then we construct the cost and mixer layers. So those are the actual time evolution operators involving the cost and mixer Hamiltonians. We construct our circuit by alternating the 2 layers with each other. Then we'll use classical techniques to optimize the circuit parameters. So as I mentioned earlier, these kinds of quantum algorithms are extremely hybrid right now, where we'll be combining, parts of it that are quantum, parts of it that are classical, and we'll see that today. And finally, we get the approximate solutions by measuring the output of our quantum circuit. So defining a cost and mixer Hamiltonian is really easy with Penny Lane because they already have QA/OA as preloaded. So it'll take in the graph that we generate, which contains the vertices and all of the edges, and then it'll suggest a cost Hamiltonian and a mixer Hamiltonian. We can define some function that generates both of the unitary operators, or the cost layer and the mixer layer, by combining the Hamiltonians that we just created and the tunable angles gamma and alpha. Now we can construct our circuit by alternating between cost and mixer layers. So as before we start off with our Hadamard gate, we have the depth of 2, which means that we apply our cost and mixer twice when we do this QML.layer step here in our quantum circuit. So now we're using classical techniques to optimize the circuit parameters. So we can define our device. We use this lightning.qubit simulator. Wires is the number of qubits. We just have to use the decorator to specify which device or simulator we're using. And then we can define some cost function of the parameters, which are our tunable angles. We put in our circuit that we defined earlier, and then we're returning the expectation value of our cost Hamiltonian. So this is what we want to minimize. And then Penny Lane has this gradient descent optimizer, among other optimizers, that we'll use to try to minimize that expectation value of our cost Hamiltonian. Okay. So we can get the approximate solution by measuring the circuit output, and we step through our different parameters until we find parameters that minimize that expectation value of the cost Hamiltonian. Okay, so before I actually show you this, we're going to go over Covalent really quickly. I know that you probably saw this earlier today, so this should just be a quick refresher, because we will be using Covalent as a framework for this QA/OA application. So Covalent is an open source workflow orchestration platform used for quantum and high performance computing. It's designed to make experiments modular. So you break it down in these different steps, just like we saw just now. So you can really easily make changes to your different steps, or take a step and extend it to a different experiment. It's easily scalable when you start getting larger data, and your experiments become really easily reproducible because Covalent will save information about your environment, what parameters you used, what hardware you used, and all of that. So Covalent exists mainly to try to cut down on the time that we spend debugging, writing, and maintaining our research code, so that we have more time to actually spend on the research itself. Covalent has this user interface that's really intuitive and interactive. So it gives you a visual overview of your experiments. So you can see how the different electrons connect to one another, and you can check on their status if they're still running, or they'll show up red and give you a specific error if there's been an error. It saves everything and anything from each electron or step in your workflow. So you can check on oh, what did I input here? What was the output of this specific part? It also maintains details of, for example, your environment and versioning, to what hardware you use, so you don't have to worry about oh, Penny Lane updated and now it doesn't work anymore and I don't remember which version I used. Covalent will store that, so you can reproduce your experiment without worrying about things like that. And it saves your hyperparameters, which is really great for when you're hyperparameter tuning and you might not remember if you've investigated these values for your parameters yet. Covalent has that saved. You just look at the output, and you don't have to run the same experiments over and over again. The UI is also interactive, so you can stop, you can start, and you can manage your jobs right from the UI. Okay, so because Covalent is used to modularize your experiments, we can take a peek at what that would look like with the steps that we saw earlier in this QA/OA application. So for each of these steps, we would just add the covalent electron decorator before defining a Python function, which just lets Covalent know that this function is an electron within our workflow. Some specific steps might be more computationally heavy, so we might want to dispatch them to some kind of remote device with bigger resources, so we can easily do that, and we'll see how to do that in the notebook. And finally, once we've defined all of the electrons in our workflow, we can construct our workflow itself with this covalent lattice decorator. And essentially what you do is you call all of your electrons in order to create the workflow itself. And then you would dispatch it to Covalent. All right, thanks. I guess I can take questions now about the talk, or we can just move on to the notebook. Stop sharing for a minute. I don't see.
Could you go over the mixer Hamiltonian? I didn't quite get exactly what it
Yeah,
is.
the mixer Hamiltonian is a little bit complicated. It's essentially so that when you're computing the expectation value of the cost Hamiltonian, you don't just have the exponent cancel it out, and then because you have the complex conjugate on one side and the other side. So the mixer Hamiltonian doesn't compute or doesn't commute with the cost Hamiltonian, which means that you can compute the expectation value. There's, if you're more curious about it, I know that Penny Lane has a write-up on QAOA and this specific problem because the math is a little bit tricky there.
Okay, thank you.
Okay, I can move on to the Jupyter notebook. So this is this QAOA.ipynb script that you should have access to. I'm just going to share my screen really quick. Okay, so can everyone see this?
Yes.
Yeah, awesome. If you could open this up on your computer as well, if you'd like to follow along. So before we get to the machine learning part itself, I just want to show you how to build a simple quantum circuit so we can see how that works. And we'll see some of the circuits that I used as examples in the talk. Okay. So first we want to import Penny Lane as QML. So you should have Penny Lane installed. Okay, and then we have this line here where we're defining which quantum device or simulator we'll use. We're using the default.qubit simulator for this example, and we're only going to have one qubit, so we specify wires equals 1. So in this function here, we're just constructing that first very simple circuit that we saw that consists of a poly X gate and then a measure of the expectation value. Oh, typo here. It should be the poly Z matrix. Okay, so poly X gate applied here, specify just that one wire that we have, that one qubit, and then measuring the expectation value of the poly Z matrix. So we can actually draw our circuit if we want. There you go. So we have some state 0, we apply our poly X gate, and then we would make a measurement of the poly Z matrix there. And then we can evaluate our circuit here. So we get a value of -1. Okay, so we know that the poly X gate is the quantum equivalent of a NOT gate. So it's flipping a qubit of state 0 to state 1. So then we should have the situation where applying 2 poly X gates would be equivalent to not applying any gates at all. We'll see that here. So here we're not applying any gates and we're running our circuit. So you get a value of 1 here, and now we're applying it twice and then evaluating our circuit, and we get a value of 1. But if you recall, when we only applied it one time, we got a value of -1. So that's good. That's working exactly as it should be. So now we're going to create this expressible entangled quantum circuit we saw that had Rx and Ry rotation gates that take in specific angles. So that allows us to look around the Bloch sphere, and then the Toffoli gate that entangles the qubits. And then we're returning the expectation value of the Pauli Z matrix for all wires. Okay, so we say we have some parameters. These are our input angles. You can put in different values if you want. You can play around with that. And then we just evaluate our circuit for those parameters. Yeah, definitely feel free to change what parameters we put in and get different values here. Okay, so we'll create now a circuit using a Hadamard gate. So if you remember, a Hadamard gate would take some input state 0 and map it to a linear combination of states 0 and 1 with 1/2 probability of being in either state. So here, what we're doing is after we define our quantum device and add the decorator here in our circuit, we apply our Hadamard to our single wire, and then we return the probability of the states in that wire. So let's see what that does. Generate that circuit. We can draw our circuit. Really simple, state 0, Hadamard gate, measuring the probability now, whereas before we've measured the expectation value. And there we go. So we evaluate our circuit and we see it's this combination of 0.5 and 0.5 because it's in the superposition of both states and probability 1/2 of being in either of them. So since it does create this probability of being in state 0 and 1 with equal probability of either, we should be able to see this by evaluating the circuit many times and measuring the expectation value of some observable. We use the Pauli Z operator here. So if we evaluate it, say 100 times, we should see roughly 50 times we get state 0, roughly 50 times we get state 1. So if we do want to evaluate it 100 times, we can add that as this little shots parameter when we define our device here. And then we use the QNode decorator here to specify that device again, returning now sampling the Pauli Z operator. And then I define this parameter values, which is just going to be the circuit sampled 100 times. Just going to add a little bit here. Works. There you go. Okay, so you can see the different values that it's had from when it was sampled. And then we can just do a histogram of those values. And we can see roughly half of the time we get 1, roughly half the time we get -1. So it's in this superposition of state 0 and 1. Okay, so now we're going to move on to the quantum machine learning application. So if you haven't done so yet, please go ahead and download Covalent using pip install Covalent and initialize it in your terminal using Covalent start. I think I actually need to do Covalent start myself, so I'll do that very quickly. Okay, so as we talked about, quantum machine learning algorithms typically are this hybrid between classical and quantum components. Here we're going to have this quantum circuit, but it's going to be evaluated using classical optimization. And so what we're trying to do is use this QAOA algorithm to find an approximate solution to our minimum vertex cover problem, where we're trying to find, okay, what are the minimum combination of vertices that cover all of our edges in this graph? You can see this is our clause that is applied to each element of our bit string set. Here's our minimum vertex cover problem. Okay, so our first step is going to be importing all of the necessary packages. If you don't have any of these, just go ahead and install it using a pip install. Okay, so this next step is a bit tricky, but I think you went over this earlier. This is setting up the Slurm executor. So Slurm is this open source cluster management service that we're going to use in order to connect to the remote cluster. So your details here are going to be a little bit different. For right now, I'll go through it. If you want to set this up when we get to the end, then we can definitely go through that part. But so your username is going to be a bit different, and same with your remote directory, and your SSH key file will be the file on your local device. But we specify all of these details for our Slurm executor, and then we define them here. So this is just saying to, when we choose our executor as a Slurm executor for a specific step in our workflow, then we just need to specify to execute, for example, that electron on the Slurm executor. Okay, so in the slides, I kind of went over the different steps in our circuit. We'll see those steps up close and personal now. So we need to divide our experiment into these tasks in order to use Covalent, where each task is a Python function here, and we just attach this should be ct.electron. We attach the electron decorator, and then once we've written and decorated all of our electrons, then we call a final function, being our lattice, that calls all of our electrons in order and returns our final result. Now, if you want to use a remote computational resource, like we'll do for one step using the Slurm executor, then we would just add to our ct.electron decorator, specify our executor here, it's GPU, there will be Slurm executor. Okay, so we have all of these modular steps in our hybrid quantum classical algorithm. Our first step is to make the graph. So this just generates, this graph that contains a certain number of vertices or nodes, and then the probability for creating an edge P at each node. So it, either connects or doesn't connect these nodes to each other, and then it generates the graph that we're going to be using for the optimization problem. Okay, so we have a get circuit. So this is the electron that defines the circuit. It includes two other functions. So there's QAOA layer that generates the cost and mixer layers given by the Hamiltonians. And then we define the Hamiltonians in the previous step using QAOA with Penny Lane. So that'll take in the graph that we've generated, and then it'll suggest cost and mixer Hamiltonians that we'll use in order to build our layers, which are the unitary gates that we're applying to our circuit. And finally, we'll make our cost function. So we define what simulator that we want to use, and then this particular step will compute the expectation value of our circuit that we've defined with a given number of layers for the cost Hamiltonian that Penny Lane has generated for us given our plot. There's a couple other steps here, and we'll see how those play into it. There's get random initialization that generates two random values between 0 and 2 pi for example, our initial values of our hyperparameters that we're trying to tune. And initialize parameter is the function where we actually take those values and create initial angles for the gamma and beta angles that we saw that are input into our time evolution operators. And then we can, for an input optimizer, we can calculate the cost. And again, if you remember, we use this gradient descent optimizer. We'll see how it behaves when we use a number of different optimizers. Just run that. Okay, so we can look at what the graphs that get generated look like using the Network X library that you should have installed. So here we go. This is our graph. That's like the most boring possible graph. It did a straight line. And then we have our cost and our mixer Hamiltonians defined as well. I'm going to run that again. So that'll change when we change which graph we have. Okay, so you can see like there's this certain probability of having an edge connected to all vertices. Sometimes they're all connected, sometimes they're not. And we've got the boring one again. Okay, so we can use this draw function to take a look at what our circuit is going to look like exactly. So we've defined our cost and mixer Hamiltonians given our specific graph. We've specified our number of qubits. We've defined our cost layer. We've defined our mixer layer. and now we're building our gate. So we're applying the Hadamard gate to all of the different wires in our circuit, and there's going to be 4 of them, which we've specified here. We apply our cost layer, we apply our mixer layer, and this is just applying them once in the workflow itself. They'll be applied multiple times. And then we compute the expectation value of the cost Hamiltonian, and here we're drawing it. Okay, so our circuit will look something like this. Have our different qubits here. We have our Hadamard gates. This is our first time evolution operator. This is the cost Hamiltonian. This is our second time evolution operator. This is the mixer Hamiltonian. And then finally, we are making a measurement of the cost Hamiltonian on all of the wires here. Okay. So we can see the functions themselves now. We have this make graph. This is not just making the graph that we saw, but it's also defining our cost and mixer Hamiltonians. This was imported from Penny Lane for that specific graph. The step is getting our circuit. So we have, for our cost and for our mixer Hamiltonians, we have to actually make the unitaries or the time evolution operators. We do that here. It's really straightforward using Penny Lane. And then in this step right here, this QML.layer, that's telling us how many times we're applying this QAOA layer here that we've defined. So for a specified depth, then we'll apply it however many times. Here, when we actually run it, I believe it's just 2, which means we're applying our Hadamard gate, and then we're going cost evolution operator, mixer evolution, cost evolution, mixer evolution, and then returning our circuit, which is what we'll be using to optimize. So we make our cost function by calling our circuit here, and for our input parameters, which is going to be our initial angle values, we're then returning the expectation of the cost Hamiltonian and trying to tune those angle values. Here's our random initialization and our initialized parameter, which is returning our initial cost function and our initial angles that are just drawn from a uniform distribution between 0 and 2 pi. And finally, we need to calculate the cost. So this is what we want to minimize, is the value of the cost itself. Just press enter, and now we've defined all of those electrons. There's finally 2 more. There's the optimization step itself. So this is the optimize_electron. So this one, if you want to execute it locally, then comment out this line specifying to use the Slurm executor and just use an electron without the decorator, and that'll run it on your local device. But here we want to try out using the Slurm executor that we defined earlier. So this will initialize parameters. It'll iterate through the optimization process, and then it will return the loss at each iteration. So you can, if it all goes well, see the value of the loss going down, which means our predictions are getting close to matching the data. And then there's this collect and mean, which just returns the mean value of an array that will get called at the end. Okay, so we run those now. We have 2 different workflows. So the run experiment workflow is the first lattice that we'll see. The second lattice will use a lot of the same electrons, but it's organized a little bit differently. So essentially, you would run this lattice if you don't really care about saving your intermediate optimization steps. So you don't necessarily care what happens during the optimization process itself, other than the loss function going down. You just want the optimization to happen. So in this case, optimization is performed in this optimize electron task. So there's no way that Covalent is told to save the input and output at each step. We'll see how to do that later, though. So as we increase the number of iterations in optimize electron, which is our optimization process, and this is the most computationally heavy step, the runtime will get long. So that's what we added the Slurm executor to dispatch that to be run on a remote device. All right, so this is finally our lattice. We call it run experiment, this first one. So now we're calling all of the different functions in the order that we need them to be called in order to build our experiment. So we have our initial values. So this was just input when we're generating the graph, the number of qubits that we want, the probability of generating, for that, I think it's generating the connectors in the graph, and which optimizer we want to use. Here we're just using one optimizer. Sorry. And then we have our cost function, our initial angles, our initial parameters. So we're initializing everything. We're running our optimization process here. We're keeping track of our loss history and our initial angles. And then when we generate this loss history, we're just appending our loss function at each step. And then if we wanted to compare optimizers, if we have multiple optimizers, then we can do that. And we'll see how to do that in just a minute here. And then this step is to compare the output of all of the different optimizers that we've used. Okay, so we've defined our lattice. If we went on to the Covalent user interface, then we would see our directed acyclic graph, or a DAG, that's showing the relationship between all of the electrons in the workflow. So you can see we start out with initializing our parameters. We send that off here. We've initialized the parameters, and then we have our initial angles. That goes to the optimized electron. We have these different optimized electrons that we're running. We're passing information along to all of them. And then that comes down to this electron list, which is the saved output. And the final step is our collect and mean. So we can see how our experiment is constructed. And when it's running, we could actually go into the user interface, look at the status of each electron, look at the input and output of each electron. And if electron has failed, it'll show up as red, and you can click on it and you can see what the exact error is. So it makes it really convenient to visualize your experiments. All right, so we've imported Covalent, and now we just want to dispatch it. So we don't need to say anything about the Slurm executor because we've already specified that with the optimized electron itself. We just need to use covalent.dispatch. This is the lattice that we want here, and these are the input parameters in our lattice. So we're doing 100 iterations here. Execute that. And then the next step is using covalent.getResults. So this step is going to take a while. And that's because it's being dispatched to this remote device because of the optimized electron step here. So you can specify wait equals true, means just wait for the workflow to finish before you're getting your results. I'm going to take this opportunity to have some water actually while we're waiting for our result. Okay. So as I mentioned, this first workflow was set up in order to take a list of optimizers and compute the mean loss between all of the optimizers. When we dispatched our workflow, we only included the gradient descent optimizer. And in our next step, we're going to see how to actually compare the output from a bunch of different optimizers. So once this finishes, we'll be making a plot here, which will be our result, which will show the value of the loss function for each iteration as we went through the circuit. So we should see that loss function going down. So the value of our cost is decreasing. Our predictions are getting closer to matching our data. There we see here. Okay, so this is the value of the cost function. This is the number of iterations. So we have it decreasing here. So our next step is to investigate the performance of different optimizers. So we just used the gradient descent optimizer, but PennyLane has a whole bunch of them we can use. So we're going to specify this list of different optimizers, and we're going to dispatch this again for all of our optimizers. So this will run the run experiment workflow for each optimizer in our list, and we do it this way so that we're getting the optimization results in full from each optimizer that we've specified. And again, this will take a minute because it is dispatching it using the Slurm executor, so it has to run it on a remote device, get the results, and send them back. So that'll take just a minute here, and I'll have some coffee. And feel free, if you want to maybe run the same thing and you want to investigate some other simulators, you can look up what optimizers Penny Lane has. You can add them to this list and you can generate the same plot, and you can see how, you know, an optimizer that I haven't considered in my list performed relative to the others. There we go. So they perform, you know, a bit differently every time just because the randomization in initializing our parameters here. But we can see that this one, this momentum optimizer, looks like it's the winner. Again, feel free to look into different optimizers and see which one performs best for you. So I'll move on to the optimize workflow. So before we had this run experiment workflow where the optimization process all happened within an electron. So we're not actually saving anything during each step in optimization. Here, say we actually do want to monitor the optimization process, then we can define a new workflow which does a loop within the optimized lattice. So it's actually calling an electron again and again. So you're saving the output at each step of optimization. So again, we have our input up here, you know, probability, number of qubits, number of iterations. 10 seems low. Do 100. Okay. Compare optimizers just as before. And then right here is where optimization is happening, where we're going through the number of iterations that we have, and we're running our optimizer at each, and we're saving the output at each so we can see a more complete picture of how the optimization process happened using this workflow. From the Covalent user interface side, it's going to look a lot different. So this is our directed acyclic graph. I've made it a little bit smaller here just because it can get overwhelmingly large when you have a bunch of different iterations. So this is just for 3, but it shows you how each of these different steps are connected, how many of them they are, how the different the workflows here or graphs are connected to one another, and what information they're passing from step to step. Okay, so here we're going to do 20 iterations, not 100, because 100 is maybe too long. We'll see. And then we're going to do the same thing of comparing optimizer results that we did before. So we compare the loss or the cost as the number of iterations increases. So take a little while again. Okay, so we just looked at 3 different optimizers. We can see the momentum optimizer, really a champ, doing great again in this round. I encourage you to look at different optimizers, see who does better, and maybe try increasing the number of iterations, see if they bottom out eventually, see what happens. So we can also investigate the angle optimization. So we want to see how these hyperparameters, alpha and beta, change as we're optimizing our workflow. Okay, so we have our optimized lattice, and we've changed it a little bit just so that we can keep track of how alpha and beta are changing. So these are our angles here, and we're just, with each step, appending them with our new value of the parameters because the parameters are updating at each step in the optimization process. So we'll query our result here really fast. So we can see our alpha is plotted in red, so that's here. The angle didn't actually change that much from our initial guess. And then our second angle, beta, is decreasing significantly with the number of iterations. Okay, so I've got a coding challenge for you here. So if you've got everything running, even if you don't have the Slurm set up, feel free to comment out that line that uses the Slurm executor. I want you to try plotting the cost versus the iterations, so like the plots we've seen earlier, for a range of different initial angles. So I'm going to stop sharing my screen for a little bit here and take some questions we might have about getting anything set up. Especially, I know that the Slurm is tricky, so Venkat and I are here to help with that. Also, feel free to toy around with the quantum circuits at the beginning. No questions here? Is everyone able to run the quantum circuits at the beginning? You were able to install Penny Lane and execute those first lines fine? Any issues there? No? Sounds like everyone's doing good with that. Okay. I'm gonna go on to our documentation to pull up some tutorials if you wanted to follow those using Covalent. Just real quick, does everybody have access to the QAOA notebook? Just want to make sure that you are able to get that. That should be in the GitHub repository. If anyone wants a really simple tutorial to follow, just with getting familiar with Covalent, in case that's easier, I'm just going to share a link here. So this is a tutorial that I wrote a really long time ago. It's called a star tracker. It's just to familiarize yourself with using Covalent itself. There's not quantum steps in here. I'll just give you some more time to experiment, and then I'm going to go over how I would do this with plotting the cost versus iterations for different angles. And feel free to make edits if you're doing this to both the electrons and to the final lattice. That's what I did in order to implement this. Are there any examples in Penny Lane related to variational quantum eigensolvers? Probably. I'll go ahead and see if I can dig that up for you. It's often called VQE. Yes. If you wanted to read a little bit about variational quantum eigensolvers, Penny Lane has this great demo that I just linked to in the chat. All right, so I'm not sure how many of you were able to get to the coding challenge versus play around with the penny lane circuit parameters, but I'm going to go ahead and share the solution that we had. Okay, so the coding challenge was to plot the cost versus iteration, so same plot that we've seen before, for a range of different initial angles. So the initial angles should range between 0 and 2 pi, and contain at least a few examples within that range. And we want to see how careful choice of initial angles affects the optimization process. So we're going to try to create a plot with cost on the y-axis and the number of iterations on the x-axis. All right. So the way that we did it was we explored 4 angle ranges. So one angle range was between 0 and pi over 2. Next angle range was between pi over 2 and pi. The following was pi to 3/2 pi, and finally 3/2 pi to 2 pi. So this involved making edits to a couple different electrons, as well as finally we'll make some changes to the lattice as well. Okay, so in the get random initialization process, previously this was just picking numbers between 0 and 2 pi, uniform distribution. Now we're modifying it, so we're picking numbers between not 0 and 2 pi, but between some lower limit and some higher limit. And we're going to set those limits for each angle range in this range between 0 and 2 pi, which means also changing our initialize parameters step. So that comes into play here, where now we also need to specify what were our lower and upper limits on the angle range that we want to explore. And then we want to return our initial angles. So I'll run that. And now we've overwritten those 2 electrons. We don't need the executor here. Okay, so we define our new workflow. It looks a lot like our old workflow. We have our input parameters here, and now you'll see we have these limits here. So showing 0 and 2 pi. Okay, that's the full limit of the angles we want to explore, and then we'll need to pass that in for each angle range that we're investigating. Okay, so we're just going to run it as before, but now we're running it different times for each angle range. So I'll run that electron. Okay, so we define this new array of limits. So rather than just being 0 to 2 pi, which is what it's been, it's just randomly initializing our angles in that range, telling it to only initialize it within these small subranges. We're going to use this atom optimizer. You can use whatever optimizer you want for this step. And this is local, so we're not actually dispatching any of this to Slurm. We're just using, our laptop for this. Okay, it's pretty fast. So this shows us in our different angle ranges how the optimization step happened, how the optimization happened. So the 0 to 2 pi looks pretty flat. There wasn't much improvement. The pi to 3 pi over 2 angle range didn't perform super well. So this is just showing you it depends what initial angles you're picking, how your optimization process is going to go. So if you want to get really deep into optimizing your workflow, one thing you might want to consider is optimizing how you're initializing it to begin with, in addition to things like which optimizer you're using. Oh, thanks, Venkat. I saw you shared the Git repo. So if you wanted to check out, the slides or the QAOA notebook we've looked at, as well as the solution should be on there too, you can go ahead and check that out. So in our last time here, you can play around a little bit with these quantum circuits up top. Was anyone able to do the challenge? I'd be curious if you had a different solution or if you explored different ranges of values or more specific values. Okay. So we can maybe alternate here and say like applying our poly X gates over and over is just flipping the value of the qubit over and over again. I don't know why it's typing wrong there. Doesn't like my indentation. We've now flipped it. And if we get rid of that line, then it's 1. So these kinds of things are really straightforward. So for here, we had these different parameters here. I'm going to change this. Didn't like that. It's because we've redefined circuit, that's why. Make sure to run these in order because we are using the same function name over and over again. Okay, so you can see, different output when we change the rotation. And then we could change, like, maybe we don't want to use the poly Z matrix. Maybe we want to do the poly X matrix for our expectation values. We could do that. And then we get these different values here. So we have our Hadamard gate here. We can explore what happens if we apply the Hadamard gate twice. Okay, so this was the Hadamard gate is what takes state 0 and it puts it in this equal superposition of being in 0 and 1. And now we've negated that and we're back into position 0. So the Hadamard gate will put it in a superposition and take it out when you next apply it. And you can, if you wanted, you can actually look at the Hadamard matrix itself and work out how that would work using matrix multiplication. So now we've got it back into being in this superposition. And we've got approximately 50-50. We can see what happens if we take this down to 10. So this is only 10 iterations. So I would say the likelihood of it being 50-50, is going to go down a bit. Oh no, that's actually really close to exactly. That is exactly 50-50. That's funny. Doesn't always work out that way. And then if we, increase this to like 300, we should see pretty close to even. We could try as well increasing the number of iterations in our workflow. So if you remember in the second workflow that we did, we ran with 20 iterations. We could take a quick look at what happens if we increase that. So I'll need to redefine our electrons because we did change them when we were doing the challenge. So we're at the optimized workflow. We redefine that. You see our covalent user interface. And now Can do it for maybe 200 iterations. So it'll probably take a long time. We might not see our results in time. Maybe we will. This might take a long time. Still going. We might run out of time before it finishes. Did anyone get any interesting results playing around with the workflow or, making your own quantum circuit?
Very little shy. Don't mind that.
Yeah, no, that's fine. Just gonna drink some water here. Oh, one of you asked about the mixer Hamiltonian. You know what? I'm going to send you a link. I know that Penny Lane has addressed this specifically. If you wanted to see the math written out, see if I can find it. Yeah, here we go. So I'm going to link to that here. So here's a really specific answer on what exactly is going on with the mixer Hamiltonian. It's a lot easier to follow once you actually see the math written down. I'm not sure we're going to get our result in time, unfortunately. Just a couple more minutes here. All right, it looks like we're running out of time here. So I am going